Science does not reward impatience. A hypothesis is not a fact. A prediction is not a proof. And yet, between what we can demonstrate and what we merely suspect, there is a space, careful, considered, mathematically sound, where some of the most consequential ideas in the history of human thought have quietly waited to be confirmed. Consider black holes. Carl Schwarzschild identified their mathematical possibility in 1916, working within Einstein's newly published framework of general relativity. John Michell had glimpsed something similar even earlier in 1783. Using Newtonian mechanics alone, he predicted the existence of objects whose gravity would prevent light from escaping. Two independent traditions of physics, separated by more than a century, pointing at the same dark conclusion. And yet, for 55 years after Schwarzschild and 188 years after Michell, no one had ever actually seen one. Cygnus X1 changed that in 1971. A stellar remnant so massive, so dense, so thoroughly consistent with what the equations had long predicted that the scientific community eventually accepted what it had been circling for nearly 2 centuries. Black holes are real. If that story happened once, there is no particular reason to believe it cannot happen again. Somewhere in the vast theoretical landscape of modern physics, there may be objects, stars, remnants, geometries of space-time itself that exist right now, waiting for the instruments and the patience to find them. They are predicted. They are, in many cases, mathematically necessary. They simply have not been seen. What are these objects? Today, we're going to examine some of the strangest structures the universe might contain, not as speculation for its own sake, but as a serious reckoning with what the equations allow. Some of these may eventually join black holes in the confirmed column, others may not. Either way, the inquiry itself tells us something important about how the universe is built. Part 1. The Architecture of Stars. To understand exotic stars, you first need to understand ordinary ones. Stars persist because of a negotiation, a constant, ongoing balance between two opposing forces. Gravity pulls inward. Pressure pushes out. The star endures for as long as these two forces remain in equilibrium. For our Sun, that equilibrium is maintained by nuclear fusion. In the core, hydrogen nuclei are fused into helium under conditions of extraordinary temperature and pressure. The radiation produced by this process, photons streaming outward in every direction, exerts just enough pressure to prevent the Sun's outer layers from collapsing inward under their own weight. This is called radiation pressure, and without it, the Sun would not exist in its current form. What changes across different types of stars is not the principle, it is the mechanism. When the Sun exhausts its hydrogen fuel in approximately 5 billion years, it will expand into a red giant, shifting to helium fusion. When the helium is gone, it will exhaust what remains of its lighter elements. At that point, without a fusion source to sustain the pressure, gravity wins. The outer layers will be expelled, and what remains, a dense, cooling remnant roughly the size of Earth, is a white dwarf. White dwarfs are no longer fusing anything, so where does their supporting pressure come from? Here, the story becomes genuinely strange. At the densities found in a white dwarf, the physics governing matter shifts from classical to quantum mechanical. Electrons, under the rules of quantum mechanics, cannot occupy the same state, cannot be compressed arbitrarily close together. The resistance that emerges from this quantum constraint is called electron degeneracy pressure, and it is this resistance, not any chemical reaction, that holds a white dwarf together. But there is a limit. Above 1.4 solar masses, a threshold known as the Chandrasekhar limit, electron degeneracy pressure becomes insufficient. The core continues to collapse. Protons and electrons are forced together into neutrons. What emerges from this further compression is a neutron star, a city-sized object containing more mass than the Sun, supported now by neutron degeneracy pressure, the quantum resistance of neutrons to being crowded together. And neutron stars, too, have a ceiling. Above approximately 2.2 solar masses, even neutron degeneracy pressure fails. There is no known physical mechanism capable of halting the collapse. From the perspective of an external observer, the remnant disappears behind an event horizon. We call this a black hole. This is the hierarchy of stellar death as we currently understand it. Each stage defined by the type of pressure that supports it. Each threshold a marker of what ordinary matter can and cannot do. That last phrase, ordinary matter, is where the story opens back up. Part 2. Stars made of vacuum. In 1959, physicist Hans Adolf Buchdahl established a constraint on any star made of what he called realistic matter, matter with positive energy density and pressure throughout. Such a star, he showed, cannot be smaller than 9/8 times its Schwarzschild radius, the critical size at which an object would become a black hole. That factor of 9/8 may seem minor. It is not. It means that any physically reasonable star is noticeably larger than a black hole of equal mass, and therefore distinguishable from one, at least in principle. Buchdahl's result, however, only applies to realistic matter. It does not apply to matter with regions of negative pressure. This is where things become genuinely unusual. If a star contains matter that allows for negative pressures in some regions, Buchdahl's limit breaks down. Such a star could, theoretically, approach the size of a black hole arbitrarily closely, becoming nearly indistinguishable from one by any external measurement. This has caused considerable frustration among astrophysicists, who now must qualify every apparent black hole detection with the caveat that it could, in principle, be an extremely compact object merely mimicking a black hole's appearance. But the more interesting question is, what would a star with genuinely negative pressure actually look like on the inside? To answer that, we turn to the TOV equation, named for Tolman, Oppenheimer, and Volkov, who derived it in the 1930s. The TOV equation describes how pressure changes as you move outward from the center of a stable star. For most stars, this is unremarkable. Pressure is highest at the center, decreasing smoothly toward the surface. For a star with a sufficiently negative central pressure, the TOV equation behaves differently. It predicts that pressure must blow up to negative infinity at some point inside the star, then flip instantaneously to positive infinity, then decrease outward to zero at the surface. This sounds, and is, deeply strange. But there is a specific case that simplifies dramatically. When the central pressure is set to be exactly equal in magnitude, but opposite in sign to the central energy density, the infinities cancel. Pressure and energy density remain constant throughout the entire volume of the star, equal, opposite, and perfectly balanced right up to the surface. Constant positive energy density paired with constant negative pressure of precisely equal magnitudes. If that description sounds familiar, it should. Those are the exact properties of vacuum energy, the ground state energy of empty space, the physical quantity most closely associated with what cosmologists call dark energy. This is how the gravistar gets its name, gravitational vacuum star. Proposed in 2001 by physicists Pavel Mazur and Emil Motola, the gravistar is, in essence, a star made of the same stuff as the vacuum between galaxies. Its interior contains zero net gravitational force, the gravitational attraction of its positive energy density precisely canceled by the gravitational repulsion of its negative pressure. No force pulls you inward, no gradient pushes you outward. If you found yourself inside a gravistar, you would float freely, as though suspended in ordinary empty space. The gravistar raises two serious questions, both of which are currently unsettled. The first is observational. How do we distinguish a gravistar from a black hole? The defining feature of a black hole is its event horizon,
a boundary from which nothing returns. A gravistar, being slightly larger than its Schwarzschild radius, would have no event horizon and could, in principle, emit information outward. It might also produce a subtly different gravitational wave signature during a merger, a signature potentially detectable by observatories like LIGO. In practice, however, sufficiently compact gravastars remain difficult to distinguish. The best current measurements constrain the radius of known black hole candidates to approximately their Schwarzschild radii, in some cases to extraordinary precision. Whether something lies just beyond that radius remains, for now, an open question. The second question is cosmological. Could gravastars be the source of dark energy? In early 2023, a team at the University of Hawaii published an analysis suggesting that the masses of supermassive black holes appear to grow over time at the same rate that dark energy would grow due to the expansion of the universe. Their proposed explanation: these objects are not conventional black holes at all, but gravastars, objects filled with dark energy, their interior containing zero net gravitational force. The response from the broader scientific community was pointed. Observational astronomers challenged the interpretation of the data. Theoretical physicists disputed the underlying mechanism. The coupling of black hole mass to cosmic expansion is not straightforwardly predicted by existing theory. The gravistar hypothesis remains neither confirmed nor conclusively ruled out. It exists in the careful middle distance where theoretical physics often works, too well motivated to dismiss, too under-constrained to confirm.
Part 3. White holes. A cone, described mathematically, is not the object you might picture. The intuitive cone, the traffic cone, the ice cream cone, is half of the full mathematical structure. Write down the equation and graph it completely, and what you get is two cones joined at their tips, mirror images of each other, one pointing upward, one pointing down. Black holes are the same. The black holes we observe in the universe are formed from collapsing stars. They are, in this sense, like ice cream cones, real, partial, bounded by the specific physical conditions of their formation. But the mathematics of general relativity admits the complete picture, the full double cone, and in that complete picture, something else appears. A Penrose diagram makes this visible. It is a technique for representing an infinite spacetime in a finite drawing, where light rays travel at exactly 45 degrees. In the simplest diagram for a black hole, region 1 is the ordinary universe. Region 2 is the black hole interior, a region from which light cannot escape because all paths lead upward into the singularity. But the complete mathematical solution contains two more regions. Region 3 is the time reverse of a black hole. It has a singularity not in its future, but in its past. Light can only move outward from it, nothing can enter. This is a white hole. Where a black hole is a region that absorbs everything and emits nothing, a white hole emits everything and absorbs nothing. The mathematics does not distinguish one as more valid than the other. They are the upward and downward halves of the same structure. Beyond the white hole lies region 4, a parallel universe connected to ours through the geometry of the black and white holes, but causally inaccessible. No signal, not even light, can travel between it and region 1. This does not mean every black hole is connected to a white hole. It means that the laws of physics as we understand them allow white holes. Their absence from the observed universe could reflect physical instability. White holes may be unstable objects that decay quickly, rather than mathematical impossibility. There is, however, a more specific proposal. Even an isolated black hole in empty space is not perfectly stable. Through a process described by Stephen Hawking, black holes continuously radiate a faint thermal emission, Hawking radiation, losing mass gradually over astronomical timescales. As a black hole shrinks, this process accelerates. Eventually, it approaches a terminal state near the Planck mass, approximately 20 micrograms, at which point our current theories become insufficient. General relativity cannot describe what happens next. We lack a working theory of quantum gravity. Loop quantum gravity offers a possible answer.
In this framework, space itself is composed of discrete, quantized units, loops, rather than being a smooth continuum. Within this formalism, the equation suggests that a black hole approaching the Planck mass does not simply vanish. Instead, it undergoes a quantum tunneling event, transitioning from a collapsing black hole into an expanding white hole, which then slowly releases its contents back into the universe over an extended period. This process has a remarkable property. The white hole, despite being tiny, can contain an extraordinary volume in its interior, stretched into a thin tube by the geometry of the transition. This means it carries enormous entropy and potentially the information record of everything that ever fell into the original black hole. If correct, this mechanism would resolve the black hole information paradox, the apparent conflict between quantum mechanics, which demands information be conserved, and the classical picture of black holes, from which information appears to vanish permanently. There is also a broader implication. In general relativity, our universe traces back to a singularity 13.8 billion years ago, the Big Bang. A stationary, uncharged white hole also has a singularity in its past. Loop quantum gravity raises a genuine question. Could the Big Bang itself be the interior of a white hole, the expanding aftermath of some prior collapsing spacetime? This is not, as it might first appear, pure speculation. It follows directly from applying loop quantum gravity to cosmological boundary conditions. Whether those boundary conditions accurately describe our universe remains to be established, but the question is at minimum scientifically coherent.
Part 4. The cosmological constant problem. There is a question in physics that has stood unresolved for decades, and the simplicity of its statement conceals the depth of its difficulty. Why is the universe expanding, and why is it expanding faster over time? Gravity, as we typically understand it, is attractive. It holds planets in orbit, binds stars into galaxies, draws galaxies into clusters. On small scales and intermediate scales, gravity decelerates and organizes. But on the largest scales we can observe, something else is happening. Galaxy clusters are accelerating away from each other. The expansion of space itself is speeding up. In general relativity, space-time is not a passive background. It is a dynamic structure, shaped by the energy and matter it contains. Mass curves space-time, but so does energy, and so does pressure. Energy density measures how much energy is present in a given volume. Pressure, in a cosmological context, measures how forcefully that energy pushes outward on its surroundings. When both are positive, as they are for ordinary matter, their combined effect is to decelerate the expansion of space. They add to the effective gravitational pull of the universe. But if pressure is sufficiently negative, if it exerts something analogous to a tension rather than a push, the equations flip. A medium with negative pressure, if that pressure exceeds the energy density in magnitude, will cause space to expand at an accelerating rate. This is what we call dark energy. We do not know what dark energy is. We know its effect. It accounts for approximately 68% of the total energy content of the observable universe, and its negative pressure is responsible for the accelerating expansion that has dominated cosmic dynamics for the past 5 billion years. Its energy density, as best as we can measure, is approximately 10 to the minus 9th joules per cubic meter, a number so small it is undetectable at any scale smaller than the cosmological. That smallness is itself the problem. Quantum field theory, one of the most rigorously tested frameworks in all of science, predicts a value for the energy density of the vacuum. The prediction follows from summing the contributions of quantum fields throughout space, accounting for their zero-point energies. The result is approximately 10 to the 45th joules per cubic meter. That is larger than the observed value by a factor of somewhere between 10 to the 54 and 10 to the 120, depending on exactly how the calculation is performed. To appreciate what this discrepancy means, consider the following.
If you were to generate 3 random numbers between -1 and +1, add them together, and hope that the magnitude of the sum is smaller than 10 to the -56th, you would be waiting a very long time. The odds are not favorable. You would need, on average, something like 10 to the 56th attempts before achieving that result by chance. And yet the universe has done exactly this, or something equivalent. The observed dark energy density is incomprehensibly smaller than the predicted one. It sits at precisely the level required for atoms to form, for stars to ignite, for galaxies to coalesce, for life to exist. This is the cosmological constant problem. It has no accepted solution. Various proposals have been offered. Perhaps there exist undiscovered particles with negative energy contributions that partially cancel the quantum field theory prediction. Perhaps there is a fundamental mechanism, some cosmic analog of a stretched spring that suppresses the vacuum energy to its observed value. Perhaps quantum field theory, for all its experimental successes, has something wrong at its foundations. None of these proposals is satisfactory. None has been confirmed. What has instead emerged from this difficulty is a different kind of answer, one that does not resolve the physics but reframes the question.
Part 5. The Multiverse. In 1987, physicist Steven Weinberg published a paper that approached the cosmological constant problem from an unusual angle. The question he asked was not, why is the dark energy density so small? It was, what range of dark energy densities would permit the existence of observers? The reasoning is called the anthropic principle, and in this context it works as follows. If the dark energy density were significantly larger than its observed value, galaxy formation would have been disrupted. The accelerating expansion of space would have overwhelmed the gravitational forces drawing matter together before structures could form. No galaxies means no stars. No stars means no heavy elements. No heavy elements means no planets, no chemistry, no biology, no life. Using observations of ancient quasars that indicated galaxies had formed within 1 billion years of the Big Bang, Weinberg calculated that the dark energy density compatible with galaxy formation, and therefore with any form of life, was less than approximately 10 to the -7 joules per cubic meter. The observed value of 10 to the -9 joules per cubic meter falls within this range. Not just barely, it falls in the right neighborhood. This correlation between the observed dark energy density and the threshold for life is precise enough to be striking. It does not explain why the quantum field theory prediction is so wrong, but it does suggest that whatever process sets the dark energy density, the value we observe is not arbitrarily selected from all possible values. It is selected from among values compatible with our existence. That selection requires there to be more than one possibility, which is where multiverses enter. The cosmological constant problem does not require coincidence or fine-tuning if we are one of many universes, each with a different dark energy density. In a sufficiently large ensemble, some fraction of universes will have values small enough for galaxies and life to form. Those are the universes that contain observers. Those are the universes where anyone can ask the question. Our presence in such a universe is not, in that case, improbable. It is a logical consequence of our existence. 3 types of multiverse have been proposed with at least some degree of theoretical grounding. The first is a multiverse separated by time. If the universe undergoes an eternal cycle of expansion, contraction, and re-expansion, ending in a big crunch and beginning again, and if the fundamental constants are reset differently with each iteration, then our current universe is simply one cycle among many. There is no confirmed evidence that the universe will eventually contract, but if it does, and if the parameters vary, this model is coherent. The second is a multiverse separated by space. The observable universe is bounded not by the edge of space, but by the edge of what light has had time to reach us from. Beyond that horizon, accelerating away from us faster than light can return, there may be regions of space with different physical constants, different effective laws.
Whether to call these other universes is partly a matter of definition. The evidence for physically distinct laws beyond the observable horizon is absent. This remains the least compelling variant. The third arises from quantum mechanics. In the many worlds interpretation, every quantum measurement causes the wave function of the universe to branch. Every possible outcome occurs in a separate, non-interacting branch of reality. Schrödinger's cat is alive in one branch and dead in another, and both branches are equally real. This interpretation is consistent with all existing experimental data. It may be the simplest self-consistent description of quantum mechanics we have. Whether it is correct remains genuinely unknown. Each of these multiverse proposals resolves the cosmological constant problem by the same mechanism. It replaces improbable fine-tuning with statistical inevitability across a sufficiently large ensemble. Given enough universes, the right parameters become unavoidable. But none of these proposals is provable by any currently imaginable method. To verify a cyclic multiverse, you would need to survive a big crunch. To verify a spatially separated multiverse, you would need to travel beyond the observable horizon and back. To verify the many worlds multiverse, you would need access to a branch that is, by definition, causally sealed from your own. All are, for practical purposes, inaccessible. The multiverse may explain everything or nothing. We cannot currently tell which.
In 1783, John Michell proposed that objects with sufficient mass could trap their own light. For the next 188 years, this remained a theoretical possibility, well-motivated, mathematically coherent, physically unconfirmed. Then Cygnus X1 was detected, and what had been an abstraction became a fact. The history of physics is, in part, a record of this pattern. Neptune was inferred from gravitational anomalies before any telescope found it. Antimatter was predicted by Dirac's equation before it was detected in a cloud chamber. The cosmic microwave background was a theoretical consequence of the Big Bang model before it was accidentally discovered by radio astronomers who initially mistook it for equipment noise. The universe, it appears, is under no obligation to announce its features immediately. It keeps its inventory on its own schedule. Gravistars may exist, objects filled with vacuum energy, mimicking black holes from the outside while containing no singularity within. White holes may exist, the time-reversed counterparts of black holes, born when black holes die, carrying with them the information record of everything that ever fell inward. Parallel universes may exist, not as metaphor or fantasy, but as a structural consequence of quantum mechanics or cosmological inflation or the cyclic dynamics of space itself. None of these has been confirmed, none has been ruled out. What they share is mathematical respectability. They emerge from frameworks, general relativity, loop quantum gravity, quantum field theory, that have been tested repeatedly and found consistent. They are not arbitrary inventions, they are implications. What the equations say is possible, the universe has sometimes, not always, but sometimes, turned out to contain. The patience required to work in this space is not a secondary virtue, it is the method itself. A hypothesis is not weakened by the time it takes to confirm, it is simply waiting. The instruments improve, the observations accumulate, the theoretical constraints tighten, and occasionally, not on any predictable schedule, but with a regularity that is itself striking, something that existed only in the mathematics is found at last to exist in the sky. What we imagine today, we may observe tomorrow. We simply do not know which day.